So take a look at how you set this up, okay? It's a very interesting setup. It is a triangle. You do have to use trig, okay? What you're going to do is you are going to set up your triangle. That is the angle at which your kite is. Your distance is S. I called it S for the shadow. That's the kite. You can't understand that. Beautiful. Okay, so here's our drawing. our our angle I'm going to call theta. This is our shadow. This is the kite string. This height is constant, so I just put the number 40 there. We do know that x is 80. We do know d theta dt is changing at a rate of negative 0.1 radians per second. Okay, so we do have to use radians in our calculation. Just make sure your calculator is in radians if it doesn't come out great. We need to find out how ds dt is changing. Okay, so the first thing you got to do is set up a relationship between theta and s. That relationship is always the tangent of theta is adjacent over hypotenuse, and you don't want, or opposite over adjacent, oh my goodness. So you don't want to use the x because they didn't give us dx dt. If they gave us the x, we would use dx dt, and we would maybe use a sine or a cosine, but we do want to use the tangent, so we just have s and 40. So our tangent is opposite over adjacent. Now I rewrote that so it's easier to differentiate as 40s to the negative 1. And then I differentiated and I got that, okay? So y, well, a derivative of a tangent is secant squared, attach a d theta dt. The derivative of this, the power goes down in front, the power goes down by 1, the 40 just stays there, multiplied by ds dt. Now, one of the things I noticed is I need theta. So let's go back for a moment. To do theta, I need to know what theta is. I know this is 40 and this is 80. 40 over 80 is 1/2. If you do on your calculator even, I would do it degrees initially. You do get pi over 3, you do get 30 degrees. The sine is 1/2 at 30 degrees if you use a unit circle. So that tells me that this particular angle is stuck at 30 degrees at that particular moment in time. So that was the weirdest thing to find. And then to find S, you just use the Pythagorean theorem. So that's how I found S. And just plop the stuff in. So the hardest part is recognizing you have to use a tangent. Anytime they use a change in angle where it says degrees per minute or radians per minute or second or whatever, you always, that's going to imply that a trig function is going to happen. So I would never give you that one like that if it wasn't like a bonus or something of that sort. But I did want you to see that there are some nasty dreads problems that exist out there. And I think that's how you do that one. Oh, it's horrible, horrible. So 3.3 is about how derivatives affect the shape of the graph. Last year in pre-calculus, we were able to graph polynomials using end behavior, using what we knew about zeros. But I told you at the time that our the heights of our bumps, our maxes and mins, the actual curvature of the graph, we couldn't do much about. So I let all that slide. We could go, yeah, it's about a rough sketch like that. In a calculus class, we know more about the graphs for the first time. and derivatives actually tell us that. So that's what we're going to use derivatives for as we go through 3.3 and 3.4. How does a derivative give us information about the shape of a graph? So this lesson's really important that you understand how this works. So we're going to talk about where our function increases and decreases, the concavity, what's called an inflection point, what's called the local mins and maxes. So we're going to find out a lot more stuff about a graph than we ever had in a pre-calc class. Now we still have to blend all that stuff we know from a pre-calc class. So that stuff doesn't go anywhere, but now we get to add more information to it to graph things more effectively. So remember that our derivative tells us about the slopes of the tangent. The derivative tells us about the slopes of the tangent. So let's highlight some stuff here. Every place that our function is increasing, our tangent lines have positive slopes. And you might recall that little graphic I had shown you where the tangent lines were going across the graph, and they were green every single time that we were going uphill from left to right. They were red every time our function was decreasing or going downhill from left to right. And then right when they hit those maxes and mins, they turned black when the slope of the tangent was 0. So please remember that the first derivative is the slopes of the tangent lines. And so where those slopes are positive is going to indicate that our function is going uphill from left to right. Where that function is going downhill from left to right, our derivative will be negative. And where it's 0, it's going to indicate that we have hit a local min or max. So the first derivative gives us lots of information about the shape of our graph. So we're going to use what's called the first derivative test. If the first derivative is positive on any interval, then our function is going uphill. So if our first derivative is positive, our function will be increasing. If our first derivative is negative, our function is decreasing. So to use the first derivative test, we find the first derivative, we make a plus or minus chart. If it's positive in that section, our function will be increasing there. If it's negative, our first derivative is negative, our function will be decreasing. So the first derivative is super useful to tell us, is it going uphill in that section? Is it going downhill in that section? What is it doing? Is it increasing or decreasing? And I've been showing you that kind of for a while because I wanted you to start seeing how that works. But this is the most formal way we've seen this presented. So let's take a look at a function like this. So we've got a fairly complicated polynomial, and we want to know where is the function increasing or decreasing. So the first step we take is we always want to find the first derivative. So our first derivative is 12x cubed minus 12x squared minus 24x. The second step is we want to make a plus or minus chart. I believe that's what it said, yeah. But what I would like to do is kind of break that step down. Like, how do you make a plus or minus chart? Yep, so the first thing we're going to do, well, we're not going to do the derivative yet, but that might come later on. It actually may be in these notes. You want to find where is the first derivative equal to 0. You want to make a number line. You want to make test values. And before we go further, let's kind of do that A, B, and C of making our plus and minus chart. Okay, so we're going to set our derivative equal to 0, and if at all possible, you want to factor. Okay, so you may notice that all of our coefficients are divisible by 12. we do have one x in common to all of those. So if there is a greatest common factor that can be removed, that's an effective way to kind of get started. If I remove a 12x from all of the terms, I get x squared minus x minus 2. And if this part is not factorable, you must use the quadratic formula. Let me say that again. If this isn't factorable, you're not done with it. You must break it apart using the quadratic formula. But luckily for us, it's factorable. This is x minus 2 and x plus 1. So we're still on part A of step 2. We need to find values where the first derivative equals 0. So we have values of 0, positive 2, and negative 1. So now we can move on to step 2b. Actually, let's make a number line chart. So give yourself some room above your number line. So you notice I have a little bit of room there. Put your values in number line order, negative 1, 0. They don't have to be spaced properly, but just in number line order. We're going to make this into a chart. So we're going to put some little lines here. And if you go back to our factored form, do you see how we have 3 factors? So we need 3 rows in our chart. So I'm going to put 1, 2 lines, so then I have 3 rows. And I'm going to write the factors over on the side. In one of the factors, usually if there's an x term, you need to include that front coefficient. So 12x, x minus 2, and x plus 1. These factors here should include all of the factors that are in that original expansion. Everything has to be there. Okay. So in 2C, once we've made our number line chart, we have to test values. So in 2C, let's take some numbers on the number line that are test values. Now, what I mean by test values is I need a number over here, a number over here, a number over here, a number over here. I need 4 numbers. A number to the left of negative 1 is negative 2. Now, you can pick any number over there. So if you pick negative 3 and somebody else picked negative 4 and I pick negative 2, we're all going to be okay. Between negative 1 and 0, there's not much of a choice. So let's go with negative 1/2. I mean, yes, there's a million choices, but something nice, there's not anything nice. If I plug in 0, between 0 and 2, why not 1? It's not a bad number to plug in. And if I plug in anything after 2, why not 3? Again, anything bigger than 2 will work. So if you want to pick 10 or 100 or a million, go for it. Okay. Now, so part 2C is to make test values. And now we're going to test them in these factors along the side. And all we care about, is it plus or is it minus? So we did this a little bit before. If I plug negative 2 into the top, I get a negative. If I plug negative 2 into the middle, that's negative 4, that's a negative. If I plug negative 2 in the bottom, that's a negative. 3 negatives multiplied together gives me a negative in that region. Okay, so if I plug negative 2 into each of those, I get negatives. 3 negatives multiplied together gives me a negative. Now let's plug in negative 1/2. I get negative 6. I get negative 2.5. I get positive 1/2. 2 negatives multiplied together gives us a positive. Let's plug in 1. Positive, negative, positive. 1 negative gets a negative. If I plug in 3, I get positive, 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 which is a positive. Now that brings us, now that we have done our chart, we have everything listed. Now we're ready to interpret our chart. Okay, so what does it mean? What do these values tell us? So let's go over to the chart. Where our function is negative, remember that indicates that our function is going downhill, it's decreasing. So let's highlight that red. Where our function was positive, it was going uphill. Let's color that in green. And where our function was equal to 0, I'm going to color in with just a little dot. Okay. So let's interpret what we know. Okay, we're going to interpret two different ways. Let's talk about intervals. Our function is decreasing. And our increase and decreasing, we never use a bracket. We always use a soft parenthesis because that switchover place is doing it. It's not either increasing or decreasing when it switches over like that. So it's decreasing from negative infinity up to -1. And then there's another little spot from 0 to 2. The union indicates we have two separate pieces where this is happening. It is increasing where we go from -1 to 0, and then also from 2 to infinity. Now, we haven't got to it yet, and I'm not sure when. That's coming up in the next little section, but I want to talk about what this tells us as far as a graph goes. So I'm going to draw underneath a very extremely unsophisticated rough sketch of the graph. So don't think this is anything fabulous, okay? So just so that my number line kind of matches it. So I know that our function I have no height. The heights are arbitrary. I'm just making a little rough sketch of the graph, okay? Our function is going downhill until it hits a height of -1. And then it's going uphill again until it hits a height of 0. And then it's going downhill again until it hits a height of 2. And then it's going uphill again. Now, I do not know well, I know, but you do not know yet how the curvature is of the graph, meaning is it curved upward there? Is it curved downward there? We don't know the heights of the bumps yet. We don't know any of that yet. But what we do know is this point here has to be a local minimum. At -1, we have a low point in the graph. I don't know what it is. We could plug in numbers. Great. At 0, we have a local maximum. At 2, we have a local minimum. And unless we have more information, unless we plug in some points, we don't know if it's the lowest local minimum or the highest local maximum. We just know it looks something like that. Okay? Everybody see how I kind of did what I did? Okay. That brings us to finding local mins and maxes. By the first derivative test, here's the part you really want to highlight. A critical number of a continuous function is a local max if it switches, the first derivative changes from positive to negative. So look right back up into my picture. See how it went from positive to negative. It went from increasing to decreasing. Doesn't that have to be a local max? That's what that first line says. If my derivative changes from positive to negative, it has to have a local max at C. If my derivative changes from negative to positive, it has to have a local minimum at C. See how it changed here from negative to positive? It has to be a local min. And if it does not change sign at some critical number, it doesn't have a local min or max there, that critical number might be doing something else. Eventually, we're going to learn about something called an inflection point. So there might be an inflection point at that particular location. Okay. So if it goes from positive, our first derivative goes from positive to negative, you have found a local maximum. Negative to positive, you found a local minimum. If it doesn't change sign, it isn't a local max or min, it might be something different. Now, let's look at our pictures at the bottom, and I want to kind of highlight the colors to kind of help it go in your brain. So if my derivative, my slopes of my tangents, went from positive to negative, you have found a local max. If my first derivative went from positive to negative, you found a local max. Increase to decrease. And I even think that in my head, up, down. It went up, then down. It's got to be a local max. If it went down, then up. If our slopes were negative, then positive. We have found a local minimum. If we found a critical number at C, but all of our tangent lines, I think she might need to go to see the nurse. You want to go see the nurse, sweetie? If we have a first derivative that is always positive, but we have a critical number at that point. This point is not a max or a min. We'll get to that. There's a change in curvature that happened, and so that's going to be a point that's called an inflection point. Do you see how this little cup is flipped upside down, but this little cup is pointing upward? That's a point we're going to investigate further. The same thing kind of happened here, but in the opposite direction. All of our slopes are negative, but we do have a horizontal tangent at that point. The curvature changed, but it is not a max or min. The curvature changed, and that is a type of point we are going to explore later on. Okay, so that first derivative being 0 doesn't always find a max or min. It may find a max or min, but if there is not a change from that positive to negative, you may have found something else. So that's a little bit about local mins and maxes, okay? So we did in the first example, it says find the local mins and max values of your function. I'm just going to copy our plus minus chart again. So you may want to do this as well. It's exactly the same problem. So same exact original function and derivative. This was our plus minus chart that went with it. This is our plus minus chart that went with it. And if we want to find the maxes or mins, I already gave you the information earlier, but let's just talk about what happens. If our first derivative goes negative, followed immediately by a positive, that has to be a local minimum, because our function went downhill then uphill. It was decreasing then increasing. So if it goes negative to positive, we know that it's a local min at that location. If it goes from positive to negative at x equals 0, it has to be a local max, because it's increasing then decreasing again. If it goes from negative to positive, we also found another local minimum. And that is what allowed me to kind of draw a rough sketch of what the graph was doing. Okay. So before in pre-calc, we don't have a very good way to pinpoint those exact bumps because we couldn't do a derivative. And so now, before we just kind of had to guesstimate where the bumps were. Now we can pinpoint exactly where they are. Okay. So in example 3, we have a new function. It says find the local max and min values of the function x plus 2 sine of x. So remember what we have to do. We have to find the first derivative. We have to make a plus or minus chart. We have to find our increasing, decreasing, and that will give us our maxes and mins. So we just have an extra 4th step if we're going past finding increasing and decreasing. So the first thing we need to do is find our derivative, which is 1 plus 2 cosine of x. So we're asking ourselves, where does the cosine of, or 1 plus 2 cosine of x equals 0? Because we need to find those locations where things are happening. So technically, that would be where the 2 cosine of x equals -1, or the cosine of x equals -1/2. Now, customarily, we want to do everything in radians here. And think about the fact that the cosine is negative in the 2nd and 3rd quadrants, right? Yeah. Cosine is negative to the left. And the cosine is 1/2 at pi over 3s, right? The pi over 3s, that's 1/2. And so we have 2 locations where this is going to happen. This is going to happen at what the pi over 3 is in the 2nd quadrant, so 2 pi over 3. And what it happens in the 3rd quadrant, which is 4 pi over 3. But I can loop around the circle again and again and again, frontward, backwards, whatever I want. So I have to put plus 2n pi and plus 2n pi. Yes. Oh, that's great. So I don't have to do that. Oh, thank you so much, because I was going to be like, that's a lot of values. We only have to look at values between 0 and 2 pi. Yay. Thank you for noticing. Please erase that. Yay. I was like, oh, okay. Yeah, I didn't either. Okay. So let's go ahead and draw a plus minus chart. Okay. I'm going to kind of go from 0 to 2 pi. So normally it's kind of arrows going to the right and left, but we need to really truncate it and stop it from here to here. Okay. And I need to put on there 2 pi over 3 and 4 pi over 3, so they go in order. Okay. I only have one factor, 1 plus 2 cosine of x. So I only need one little row there. But let's make it look a little more chart-like. And then our test values. Now, 2 pi over 3 is 120 degrees. So I need something between 0 and 120. So why not 90? You know, that's a point. And so 90 is pi over 2. Now, 2 pi over 3 and 4 pi over 3, that's 120 and 240. Right in between there is 180. Why not? So let's go pi. And then 4 pi over 3 and 2 pi over 3. Between 240 and 360, 270 is a good one. Let's do 3 pi over 2. Okay, so pi over 2, the cosine of pi over 2 is 0 times 2 is 0, plus 1 is 1. That's a positive number. The cosine of pi is -1. 1 plus 2 times -1 is -1. That's a negative number. 3 pi over 2. The cosine of 3 pi over 2 is 0 times 2 is 0, plus 1 is positive. So we've made a plus or minus chart. So let's kind of highlight our chart nicely for ourselves. So it's negative in here, positive over here, 0 here and here. Okay, so now we're going to analyze what happens. It is increasing from 0 to 2 pi over 3, and also from 4 pi over 3 to 2 pi. It is decreasing from 2 pi over 3 to 4 pi over 3. Okay. Now we were not asked about where it was increasing or decreasing. We were asked about, do we have, or can you find local mins and maxes? So here we are increasing, followed immediately by decreasing. What is 2 pi over 3? It's a local max. So we have a local max when x is 2 pi over 3. Now, if we go to the next one, it was decreasing followed by an increasing. What do we have at 4 pi over 3? We have a local min. So we have found our local mins and maxes within that interval. Okay. So at 2 pi over 3, we have a local max because it went down then up. At 4 pi over 3, we have a local min because we went, up then down for the local max and down then up for our local min. Okay. You can always check your work in Desmos. So our original function is x plus 2 sine of x. Isn't that cute? Where's the wavy brackets? This one? Okay. And I'm going to go from 0 to 2 pi to kind of finish that off for us. Okay. And 2 pi over 3, think of if it didn't show up the pi's, if it showed a digital, a value, that's something like 6.28 divided by 3. And the other one is something like 12 point something divided by 3. But anyway, you can see we got the correct answer. There was a local max at 2 pi over 3. There was a local min at 4 pi over 3. Desmos will always give you the ability to tap on the local mins and maxes so you can verify your algebra with Desmos. You can't rely on it because you can't use it on a test, but you can definitely check your work with Desmos. It should verify the algebra is correct. Any questions about example 3? Okie dokie. So next, we need to talk about curvature. And I think we're going to stop here just because we just won't have enough time. But now, for the first time ever, we're going to talk about the curvature of the graph. What does it mean if our tangents are below the curve versus when our tangents are above the curve? So that's what we will talk about tomorrow.